Okay, so um, today I'm going to finish up this section of the course where we're sort of talking about things that move around, and lately we've been addressing the sensing issue. There's a lot more to talk about on this, except that for the purposes of this course, we're not going to go there. And starting tomorrow, we're going to be peeling back the hood a bit on what is going on with this random, or technically pseudo-random stuff, and how to kind of basically what's been going on. We've been kind of using that kind of those things for a while, and tomorrow we're going to see at least a little bit about what's going on under the hood for that. But for today, and then after today, I'm finished talking about it at you, but there's going to be one more little fun thing I'm going to have for you about this. Okay, and then so today I'm going to look at kind of three ways of looking at this. I'm going to explicitly show a couple of glimpse models for this detection. The thing about the ideal thing is, if you notice, our basic approach here has been to to have these events. Part of the advantage, hopefully you've seen some of the advantage of this over a code time step approach. Not the least of which is that when you're going to a destination, you can actually get there in the right amount of time. And you don't have to kind of fiddle around with, okay, did we miss it or did we not? The second is that even though the location of your units are not part of the explicit discrete event state, if you have an equation of motion, and we've been using a simple equation of motion, but there are more complex ones that can be used, then you can identify where the unit is at every point in time, not just at the discrete ones that a time step model provides. And so we've seen that kind of the mover idea is able to change its movement state through these, basically through the start move and end move events. As we'll see, they're just for kind of avoid excessive extra stuff. It turns out that we're going to have the stop event that you may have been wondering about is kind of the key one. And in the exercise I have for you, we'll hopefully explain that. If not, then, well, I'll briefly do it here. That since our typical paths will whether it's a random mover manager, a path mover manager, or whatever, we get an end move event, but if we're in an intermediate waypoint, we're going to immediately change direction and do another one. So if we work off the end move event, then what we're going to do is we're going to sort of say, okay, well, now we're stopped. We're going to update all of our state, and then we're going to immediately change all that because we're going to make a turn. And so what the stop event does is the stop event says, okay, well, don't worry about the end move event because there's going to be a start move event happening right away. So we're not going to focus on that. We're going to focus on the start move event, and then the stop event is when we're actually going to stop for a while. And then we can say, okay, now we're actually stopped, because so that's basically what that is about. Now we've seen that the referee guy is what handles these enter and exit range events, and And as we've seen, the simplest version, which just has one target and one sensor, again, that is more for educational purposes. But the final piece is this time between when we enter and we exit. And, and so there the idea is a time to detection. And if we can model that as just sort of a single value, and there are some cases where it can, that is the most effective and efficient way of doing that. So just to kind of remind where everything is. So we have a mover. Now none of this is connected to the specific implementation. So I've done the simplest one over. Currently, you're doing a simple one, which is more complicated than the simplest one. So we have the sort of the mover is responsible for its movement state, and then it has a mover manager that kind of manages all that. But basically, at the start and start, move, end move, and stop events. And then what we've been looking at is sort of a sensor actor who is going to keep a list of contacts, that is things that sensor has detected, and it receives detection and undetection events. It doesn't do them themselves. Now, in the simplest version that I presented, the mediators have had some of the parameters, and that was just to kind of keep things simple, to save me work, but that same criteria doesn't apply when I make you do something. So, so in the way that this will typically work in the next iteration, which you will see, is that the sensor, now we will have different classes of sensors that will have different parameters. So we'll have one for each of the three different ones that we've seen. The referee for the entry, and then the mediator is the one that actually implements the rule for detections and undetection. That's where it actually happens. That's that third party that is necessary because it can't be the target and it can't be the sensor. It could be the referee, as the very first iteration was, but you saw the problem with that. The problem with having the referee actually do the scheduling, the detections and undetections, is that we have to kind of bake in what that rule is, and because there's so many different there are many different rules. We don't want to bake that in, so we take that out and throw that over to the mediator. What we've seen so far is sort of three very simple sensor mediator pairs, and this is so we'll have a cookie cutter where the time to detection is 0. So as soon as we step into the cookie where they see you, step out, you lose you. The next most complicated one is just a constant time. So this is just the response time in order to detect it. And then unlike the way we've been doing it so far, it will be a parameter on the sensor. So we'll have like a constant time sensor and a constant time mediator pair. That's typically the way this is going to work. And then the final one, the constant rate, and hopefully after today we'll understand why this is called a constant rate. I think okay, well, I'll have to do that by hand, kind of. And that's where the time to detection is an exponential with a certain mean, or the mean is the mean time to detection. And again, that will be a parameter on the sensor. But the mediator is going to hold this exponential random variable for the randomness. So that's the way that's going to work. And we'll see all that at some point. But sometimes it's not either not possible or practical to come up with something like this. So let's and the way that this is often thought of is in terms of these things called glimpses. And so, if you think of your simple, say, ground-based radar, or, got a little thing that spins around. Each of those, each time you kind of potentially ping the target, it's like a glimpse. So once you're within the range, in other words, once the target is responding to the energy that's being put out, and you're getting the return, then the idea is that you're periodically glimpsing this thing. And so the simplest version of this is that at every glimpse, you detect the target with a certain probability P. So, I mean, that's fairly intuitive? Right, okay. So, what does that look like if we were to try to implement that? Well, if we were, and now again, in the implementation, the parameters are going to be, or at least the probability of detection, it would be on the sensor itself and not the mediator. But this would be the way that the mediator looks. Okay, so it would here enter range with the sensor and the target as its arguments, and it would have a oops, I forgot the parameter. Delta T, which is the time between your pings. So, so you ping, and then so we have a uniform 0-1 random variable probability of detection. So as we've seen in previous event graphs, if we want to capture a certain scheduling edge occurs with a certain probability, this is the way we do it. So we have a uniform 0-1 random variable. We have a probability. So if every time we kind of hit this, we generate a new uniform. And if it's less than a probability, then we schedule a detection, and then this would be the same as we've done before. This would be actually on the sensor, passing the target as an argument. But if we miss, then we simply schedule another ping, but with a delay of delta T. So, so basically once, and we only do this once we enter the range. So once we enter the range, we just sort of start pinging the target, flipping a coin each time. And then once we detect it, now we stop. I mean, physically you would kind of keep doing that, but at this point, there's kind of no need. Now, what we're doing is, once we detected a target, we're not sort of trying to detect it anymore. It's like, yeah, I see you, I got you. And what we're implicitly also kind of doing is kind of tracking the thing. And the thing is this, is that intuitively, the probability of detecting a target before I've detected it ought not necessarily be the same as once I have detected it. I mean, so think of, supposing the sensor is, you're like an observer and you're kind of looking out and you don't know if there's anything there. So you're just kind of scanning and looking around. And then all of a sudden you see something. So now once you've seen it, maybe you sort of keep scanning, but it's like, if I see this target that I'm looking for, then the fact that I see it is kind of going to, when I go looking for it again, it's going to kind of, I'm going to kind of internally do a bit of dead reckoning. Okay, I saw it around here. So it's like the chances of seeing it again a short time later is going to be much greater than before I even saw anything in the first place, because I didn't even know if anything was there. So what we're doing in this, and again, this is an assumption, is we're assuming that once we have acquired a target, that we're sort of we're keeping track of it. That's an assumption. It may be that we're kind of losing it. Again, that really hasn't been studied that much. Okay, so and this is how the listener for this would be kind of working. Keeping in mind that the glimpse mediator is kind of directly impacting the sensor. So we have the referee who's listening for a sensor and a mover, and In the referee that you'll do, we'll have multiple versions of these. But then our glimpse mediator is listening to the referee, and it's listening to the referee to hear these enter range events and also exit range events. So similar to the other case, we have the same situation on the exit range. In other words, when the exit range occurs, that is when we hear it from the referee, we've either detected the target or we haven't detected the target. So if we have detected the target, then we schedule the undetection, in this case immediately. But if we haven't detected it, then we have to cancel any detection which is pending. And now in this case, there are kind of two reasons why we may have not detected the target. One is, well, we may have the pings may have worked, but the detection is scheduled after after it's out of range. But the other is that we've been pinging it and we've just never seen it in the first place. In that case, the fact that remember that when we go to cancel an event, if that event isn't on the event list, then there's still no harm, no foul. So. Okay, now, darn it, I thought I had a slide for this, but I don't. So I'll have to do this sort of by hand. Is it intuitive that since we are periodically at fixed intervals, we're sort of pinging the target and detecting it with a certain probability? Is it intuitive to call that a constant rate of detection? Because the probability isn't changing, remember. In other words, every fixed amount of time, we're detecting it with a certain probability. And that's in other words, the rate at which we're firing that target is constant. I mean, that should be sort of intuitive. Right? Okay. So what we essentially have is a sequence, and I'm going to number it the usual way, of random variables that are either, let's say 0 or 1. And it's 0 with probability 1 minus p, and it's 1 with probability p. And that sequence of that type of random variable has a name. You remember the name? I know it's been a while since. Bernoulli, our friend Bernoulli. I don't know if I'm spelling it right, but this is a sequence of Bernoulli random variables or Bernoulli trials. And this is something that basic probability classes really like, because you can kind of play around a lot with this when you're not playing with your balls and urns. Okay. So this is a Bernoulli random variable whose parameter is p, and this is a well-known thing. And so one of the derived random variables for this is that how many, that is the number of trials to success has a name too. Close. The binomials, if I have a fixed number of trials, and that's the number of successes in n trials. So there I have it, n, but the number of trials to success, but that's the right idea, but it's called the geometric. Did we talk about geometric? Yeah, so it's a geometric with parameter p. In other words, sort of x I'm sorry, well, I don't want to call it, I've already used X. I'm going to call it, let's call it N. If I say, how many pings am I going to take until I actually acquire the target? That's going to be a geometric random variable. And so if I wanted to do the same thing as I'm doing here, but instead of doing the ping, I want to use this approach. Instead of having an exponential random variable, supposing I use a geometric random variable, and I'm doing it every delta t time units, where n is geometric. So what I can do is, instead of doing all this pinging, I simply generate one geometric random variable, and now the time until that happens is going to be the time between the pings. So this is my actual time to detection. And that is, that is exactly, I mean, there is literally no difference between this and this. Here I'm actually performing the Bernoulli trials by flipping a coin. And here I'm saying, well, hey, that's just a geometric random variable. I'm going to generate one and just schedule the detection after this delay. And, so intuitively, so if we are detecting at a constant rate, then this is what's happening if we're doing a glimpse. And just by the by, one of the advantages of this, notice that there's no constraint on what the time between the pings is. So if consider this, is that if we're in a time step model, our time, and we want to do this, our time between pings has a minimum of the size of the time step. So if our time step is, say, 5 seconds, then I can't ping any faster than 5 seconds. It's literally impossible in that, in that world. But what if I want to ping faster? What if I want to ping every second? Well, in that world, you can't do that. In this world, we can, because we can set this to whatever value we want. And furthermore, if there are other, even if we have to do sort of time steppy like things within our model, we can do them at a rate which makes sense for that particular thing. So if I have one sensor that's maybe glimpsing at one rate and another sensor that's glimpsing at another rate, then regardless of how they're related to each other, I can simply set those as parameters to an arbitrary value. So even if I'm doing this, I'm actually in better shape if I'm doing this within a discrete event context. And the final thing is this, is that what you may remember is that the mean, well, there's a relationship between the geometric distribution and the exponential distribution. So the mean of the geometric is 1 over p, I believe. It's either 1 over p or 1 over minus p. So let's just say it's 1 over p. So so the expected value of this would be delta t times the, because that's just a constant. And that's approximately equal to an exponential with that meaning. In other words, the exponential one that I was calling a constant rate is constant rate because of this relationship between the two. That if I'm doing kind of a constant pinging rate, then it's really statistically almost indistinguishable from an exponential. So aren't you glad I cleared that up? I know you were wondering about that. Okay, so, well, now there's something about the constant probability that should be a little bit concerning, which is, intuitively, if we have a target that's farther away, probability of detecting ought to be different if the target is closer. So intuitively, that's certainly true. And as so, what if the probability detection depends on let's say the range? And this is a typical thing. You'll have these tables where you say, okay, if the target is within this range, then hit this probability. If the target's with this other range, you'll have this probability. And so you have this kind of it's called wedding cake thing, because if you kind of look at it from the top, kind of where you have these kind of rings. And so the probabilities are ideally increasing. That's not always the case, because there are situations where if you get too close, then it gets harder for some reason. But usually the probabilities increase as you get closer. So what that means is that we can say define our series of ranges, and for each of the ranges we have a probability. So probably might have to add an extra. But basically, these when we're within a certain range, then we have that certain probability there. And just what we need, therefore, that a parameter would be some kind of table or way of saying that when the target is this distance away from the sensor, then we can grab the probability. So there are a number of different ways of doing that. The simplest would be just just a simple map. Although there you have to, even in that, you can't just kind of look it up. You'd have to kind of have ideally you'd have a sorted map where the keys would be the different ranges, but then for a given range, for a given ping, we would have to, our probability now depends on both the sensor and the target. And if all we're extracting from that is the range, then we'd have to kind of go into our map, find the value of the key that it was between, and then apply the right probability. So here, every ping, we're going to have a different probability. And so there isn't a nice, neat formula for this. In certain cases, there actually are, because you can, there's an interesting integral you can apply to this, but that's a little bit beyond the scope of what we're doing here. So, so in this, just like the other case, now we're pinging it each time with a fixed time between pings, and but at each ping, we have our sensor and our target, and so we can say extract the range, but we could also extract other parameters from it. In other words, that probability could be this could be just any function of our sensor and our target, and that could include the range. It can include it can include other other properties. So typically, like in a in radar, there's this concept of a radar cross section, which is kind of how you kind of see the target from the perspective of the sensor. But as you see, the structure of the event graph is pretty much the same. All we would need is just this additional data to do that, which we're not going to, I mean, we're not going to go that far. Now, the final thing I want to talk about, well, before I go on, any questions about any of this? I mean, this approach allows, almost infinite ways of, kind of honing in on more precise ways of the sensor and the target are interacting. So I like the simple ones. I found the simple ones to be very useful. There are, there have been a number of cases where the basic approach has been applied using complicated, much more complicated situations. Two in particular that were done by students. there was one in which the Army has an algorithm called Acquire, which is their favorite thing. Very complex algorithm. And so so basically what we did was we implemented that and then sort of, well, I'm going to use the word train, but not in the AI sense. So we basically fit a statistical probability distribution to the to experiments using the Acquire algorithm, and then came up with a very simple version of that, which acted almost pretty much the same, except was much more efficient. The other one, there was a very detailed one that used radar cross-section and radar range equations, fitting them to, actual targets. And that was a very interesting PhD dissertation. It was part of the PhD dissertation. So the point is you can kind of go way down this rabbit hole, but I'm not going to make you do that. The final thing I want to talk about, actually kind of circling back to, I hope you're getting a sense that we're just seeing some of the pieces to this. When you start to put this together, the next logical step is, okay, now that we've detected a target, now what? We could spend the whole quarter just on different ways of expanding this. There have been some models where this has been kind of taken all the way down there. It's just that it starts to get complicated because we now have to start having components that are making decisions about this. But we also need the pieces that kind of put it together. So what this piece is what I call the simplest intercept mover manner. So we detected a target. So what we want to do is we want to intercept it. Okay, so what might that be? So again, we're looking at the simplest case. So our interceptor, it's located at the origin and has a given speed. And I think I call that, I give it a subscript I at some point. And then at time zero, now we're going to detect a target, and the target is going to be located at a certain place and traveling at a given velocity. So we're using, so it has an equation of motion that we can utilize. And so what we want to do is we want to intercept this stuff. So what do we need? Well, first we need to determine, can we? I mean, the thing might be going too fast, might be too far away, whatever. But if we can intercept it, then how can we figure out how? In other words, the two things we want to know is it when can we reach the target and where? In other words, it's well, kind of looks like this. So here's our guy. I mean, presumably there was a sensor that's not being depicted here, but we've detected it already. And here's the target. Here we are at the origin. And always start with this. What I found is if you can't, if you can't do the simplest thing, then what hope do you have for the most complicated thing? That's something that unfortunately DoD doesn't always realize, especially when they're acquiring simulation models. There have been simulation projects, I won't name any names, but that have literally spent millions, if not billions of dollars trying to model everything and failing spectacularly. So if you try to model everything, you're going to model nothing. So, I mean, that was one of the things that convinced me of this iterative approach. And I hope I've convinced you. And if I haven't, then that's okay. Just don't tell me. Okay, so we're sitting here at the origin. We see this target and it's kind of going like this. And so it's like we need to figure out, can we kind of set assuming that we're going to assume they keep doing what they're doing. Okay, again, the simplest assumption. So you're thinking, well, what if they turn? What if they do something else? Well, that is an issue, but if we can't solve this issue, then there's no point in even considering that. So now how do we move? We move by having a starting place and a velocity. Those are our states. And so we're starting at 0, and we need to figure out what is our velocity, or like, what is this intercept point? And the problem is that we know our speed, but we don't know the velocity. So that's, and we don't know where this intercept point is, and we don't know how long this is going to take. So we got a lot of unknowns here. And so is it possible to unravel that? So if it's possible, then this is what it's going to look like. Right. So now let's see if we can find the intercept. So we need to find the time and the velocity, such that if we travel at this velocity, if this is our equation of motion, again, and notice that because we're at the origin, we have one less term. That's just to make things simple. So at what time, if we travel at this velocity, will we be equal to the this, which is the equation of motion of our target? And the problem is we don't know t, or we don't know our velocity. But we know our speed. Okay. Now let's assume for now that we're faster than the target. And we can kind of look at that later, but that just for simplicity's sake. I mean, if we're not faster than the target, then it's like, what are the chances? Think of, well, I mean, if I'm a cheetah and you're a gazelle, then I better be faster than you are, at least in the short term. Otherwise, why bother? Okay. So okay, so this is the speed of the target, and that's going to be the magnitude of the velocity. And so from this equation, if we take the magnitude of both sides and square it, and then expand it all out, remembering the binomial rule for vectors here, we now have the fact that the magnitude of our velocities is simply our speed. And so when we unravel this, we have a quadratic equation in which we know the speeds, we know everything here except for t. And now this is a quadratic equation. We can, basically, we know everything in that, everything is known. And then if we unravel that, the solution now is, it knows that there's no negative here, just because we moved everything over to the other side just for this. Remember, we assumed that we were faster, so this is a positive quantity. This is a positive quantity. Everything inside is a positive quantity. So actually, as long as we're faster than the target, then we're always going to get real roots. And so, in fact, we're always going to get at least a positive root, but it may be kind of big. But the earliest time is the smaller of the two of the positive roots. So if we have a negative and a positive, then we have to go with the positive. But if we have two positives, you want to go with the earliest one. Okay. And so now the thing is, okay, so now that we know the time, so now where is it? Well, the intercept location is we simply plug it into our equation of motion of the target. And so this is our intercept point. And so so now our we basically do a move to at this intercept point. And we'll see that our velocity would be simply, well, in this particular case, it would be that intercept point over its magnitude times our speed. So as long as we're faster, then we know we can always catch it. Okay, so now let's look at some assumptions. Now, even if we're slower than the target, then as long as that determinant is positive, we still could do it. Okay, so notice that if we're smaller, then now this quantity is negative, which means that we could get a negative thing. And if this whole thing is negative, then it's not going to be possible. But okay, what is a situation like that? Well, if we're here and our target, even though it's faster, is maybe heading towards us like that, then we may have a shot. And in fact, the if you remember, this inner product of things is kind of the key there. Oops, how did that happen? This should be okay. What if they're exactly equal? So here's notice here that the difference was in the denominator, and you generally don't want to divide by 0. Not a good idea. So that isn't going to work, but it turns out then things just really simplify, because if this is 0, this goes away, and so we're just left with this. And so we can, so if they're exactly equal, then it turns out that if we're heading in the right direction, that is, if we're not kind of heading away, then it's possible for us to catch. In other words, if that inner product is negative, then the negative will become a positive, and so we actually can catch. Okay, so in other words, we now, for all possibilities, we have answered the question: can we intercept it? Okay, so whether we're faster, slower, or equal, we can determine if we can, and if we can determine the location, and we also know when. Yeah. Oh yeah, yes. Yeah, there should be it's the inner product X. Yeah, thank you. Yeah, just basically this piece here. Thanks. Okay, so if our interceptor is at the origin, then we've completely solved this. We say, well, what if it's not at the origin? Well, as we've done before, instead of being at the origin, if we look at the target's location relative to the interceptor and use that instead, then everything applies exactly as before, because in the interceptor's frame of reference, it's sitting at the origin. Just that we are all at the origin in our own frame of reference. Okay, what was the other assumption? That the time was 0. Well, what if the time isn't 0? Well, remember, and then this is one of the advantages of the whole discrete event thing, is that what we have computed is the delay from our current sim time. And since our basic operation is to schedule an event a certain amount of time in the future, then what we have computed is the delay from the current sim time. So if we were to say move to that, then that would be the delay from the current sim time. So the fact that we assumed it took place at 0 is completely without any loss of generality. Now, let's see, that's okay. Yeah, so here's how that might look. So if our interceptor would be kind of it would have a mover, we kind of have a sensor, and then we would put this into a mover manager now. And so that mover manager would implement this logic, to either have this say, okay, it would basically do this computation, figure out whether we can detect it or not, can intercept it or not, and then schedule the move to, if possible. And remember that it was since we're listening, the mover manager now is not just listening to the mover, it's listening to the sensor. And so when the sensor has a detection event, then we hear that. And in case you were wondering, that's why in the mediators, we did a wait delay on the sensor so that if somebody else wanted to hear that detection event, they could. Otherwise, because heard events are not dispatched to listeners. Okay, so now, well, what if our interceptor is actually kind of doing something? Maybe it's patrolling, and then if it sees a potential thing, it goes to intercept it. I mean, a number of years ago, I had a student who was modeling patrol boats that were kind of watching out for, potential bad guys, and then kind of going to just sort of stop them. Well, in that case, we would need to basically unhook the other one until the interception is complete, because it might have like an end move event on the event list, and so we can't well, the event list doesn't know any better. So if I have two end moves, then it's kind of jumping around from place to place. We basically unhook that until the interception is complete. And so for that, we would need an additional module initial component that says, okay, decide to do this or not. And then, well, what about the interaction? So maybe our interceptor is a missile. And so now what? Well, now that we've shot the missile has actually maybe reached it. And then now what? Is it damaged? Does it destroy it? Okay, we would need additional components that say, okay, when there's when this missile hits this target, what happens? Maybe we just cause it to stop, like that was the case in the patrol boat thing. There was sort of a potential threat, and you just kind of we just made them just stop, and then once you stop, then maybe something else would happen. And so as you can see, like once you start pulling on this thread, all of a sudden there are the types of things that you need to capture just kind of start to expand. And so for our purposes here, we're gonna stop right there. There's again, like there's gonna be one more thing where I'm gonna have you implement sort of the next generation, as it were, of the sensor mediator referee thing, having already implemented the mover manager stuff. And tomorrow we're going to start looking at random variables.